In this lecture, we are going to discuss the elementary particles and the possible allowed reactions are whether the given reaction is allowed or not, that can be discussed in detail. But in my previous lecture, I have discussed in detail about the how to categorize the elementary particles. The elementary particles are broadly categorized according to its interaction. It is a weakly interaction, they are called leptons, and the strongly interacting particles are hadrons. And the leptons are the electron and the associated neutrino, muon and the associated neutrino, and tau particle with its associated neutrino. They are leptons. And the hadrons are categorized into two groups. One is baryon, another one is meson. A meson according to the spin. When spin is 0, they are called mesons. The pi mesons, k mesons, and eta 0 mesons. They are a meson particle. And here, according to the baryons are categorized into two groups. One is according to this spin. So the nucleon and this is sigma particle and this hybrid. This belongs to one group. And for a spin 3/2 and the delta particles and sigma, psi, omega hybrids, they belongs to another group. Now here this lambda particle, sigma particle and the cascade or psi particle and the omega hybrids, they are the hybrids. And all these group, the k meson, the k plus k0, this subgroup, k minus k0 minus the bar subgroup, lambda 0, sigma particle and psi particle, omega, these all a different category called strange particles. And now these particles, they are categorized. One is according to the spin 0 particle is called a meson. So if you draw the third compound of the isospin, which is I3 or T3 along the x-axis and the hypercharge along the y-axis, then according to your value I3 and the y value, you can draw a hexagon. Now here this is one particle, this is second one, third, fourth, fifth, sixth, and at the center there are two particles. There are 8 particles. So this is a octet particle and the spin 0 and parity is minus. And this can be drawn according to the SU3 symmetry. So we have last lecture we have discussed in detail about the SU3 symmetry. As per using that one, the particles are classified in this way. Similarly, the baryon particles, they are grouped into two. One is according to the spin, and the angular momentum, the spin angular momentum is half, and the parity plus, which is one group called as octet, and another one is a baryon, which is having spin angular momentum 3/2 and the parity plus, which is called as a decouplet. Now here in the octet, so you have 8 points. So again, if you I3 y can be calculated, that was discussed in previous lecture, and according to this hexagon can be drawn. So you have 8 points, corner point 6, 1, 2, 3, 4, 5, 6, and the center there are 2 particles. So the particles are represents these points. So proton, neutron, sigma minus, cascade minus, cascade 0, sigma plus, sigma 0, lambda 0. So according to the value I3y, we can fix this point. Similarly, for baryon, the angular momentum 3 by 2 spin half decoupled. Here, if you plot a graph between I3 and Y, you have the delta particles can be arranged here and here, sigma minus, this is xi minus or cascade minus and omega minus. This point is omega 0 and sigma. So, since you know I3 and Y, using this you can draw 10 points here, 4 plus 3, 7, 9 and 1, there are 10 points. So, this is a decoupled. Now, there is a relation connecting the charge. So, this is a formula, Q is equal to I3 plus B plus S by 2. And I3 is the third component of the isospin, B is the baryon number, S is the strangeness number, B plus S by 2, and B plus S is called as the hypercharge, Y is called as hypercharge. So, I3 plus Y by 2, and I3 is Q minus Q bar. Q is the charge of a particular particle, Q bar is the average charge of the particle in the group. And so, using this formula also you can calculate I3, and 2I plus 1 is equal to, again, N is the number of particles in the group. So, using this, the isospin quantum number, that number isospin quantum number can be also calculated. So, using this formula also you can calculate the charge I3, I and Y. Now, remembering this diagram is much more easier when compared to remembering the numbers formed in the table. So, there are 6 tables are available, and all the 6 tables, the charge, baryon number, I3, strangeness number, Y charge, or the hypercharge are given in all the 3 tables. But remembering that all the numbers in the table is somewhat difficult when compared with this diagram. The diagram can be easily remembered because this is this one unit is minus 1, this is unit is plus 1, this is unit is minus 1, and this is plus half, minus half. So, from this I3 value and hypercharge value you can fix these particles. Similarly, this diagram can be easily remembered. This diagram can be easily remembered. So, once if you remember all the 3 diagrams, you can easily apply the numbers in the diagram to find whether the reaction is allowed, or you can find the missing particles, and also you can calculate the content of the quarks. First, we will discuss the questions, because all the questions they are going to discuss are much more important for NET as well as GATE examinations. Now, let us consider some few problems, and we will discuss how to apply these formulas as well as these diagrams. Which of the following reactions are possible and which are not? Give reasons. Now, here the first equation is mu minus muons, and then this is a decay equation, which is E minus plus neutrino associated with the electron and the antineutrino associated with the electron. Now, let us first have to find the charge on both right side as well as the left side, and the delta Q is the difference of charges from right side to left side. The difference is 0, then that means the charge is conserved. So, the before the reaction the charge, after the reaction find the charge, they remains the same. The conservation of that means there is a conservation of charge. So, the conservation of charge must be satisfied in order to satisfy the reaction, allowed reaction. So, first you write down Q value. This is the charge, Q value first. Here minus represents the charge is minus 1. So, for electron E minus, so there is a charge is minus 1. Neutron as well as antineutrino, the charge is 0, 0. So, both side and right side as well as the left side, the value of Q is equal to minus 1. So, therefore, the difference in charge Q is equal to 0. Similarly, find since these are leptons, because all these are leptons. So now whether you have to check whether the lepton number is conserved. So L mu, the lepton number associated with the muon, which is here is equal to 1. For muon the lepton number is 1, this is 1. For the lepton number associated with the muon, this side, since this electron, this is 0, and this is electron, neutrino associated with the electron, this is 0, this is antineutrino associated with this one is 0. So L mu, one side is 1, the other side is 0. So the delta L mu, the change in lepton number associated with mu is 0. Similarly, if you find Le for mu minus particle, this is 0. For the electron, this is plus 1, neutrino 1, antineutrino minus 1. So for the lepton number, for the antiparticles, the lepton number is minus 1. For particles, this is lepton number is plus 1. For antiparticles, lepton number is minus 1. So for antineutrino, this is antiparticle, therefore this is minus 1. So here, once if you add on the right side and left side, and you find that this is right side, this is plus 1, left side 0. So the change in lepton number associated with the electron, which is not 0. Therefore, the conservation of lepton number is not satisfied, and therefore this reaction is not possible. If we take the example 2, question number 2, here mu minus, this decays into E minus plus nu E bar plus nu E. This is antineutrino associated with the electron, and this is the neutrino associated with the muon. Now here the charge value for this mu minus is minus 1, here charge is minus 1, here charge is 0, 0. So both sides equal charge, minus 1, minus 1. Therefore the change in charge delta Q is 0. Conservation of charge is satisfied. L mu, here this is 1 for muon particle. For electron, this is for antineutrino, this is minus 1. For neutrino, this is plus 1. Whereas for electron, this is 0. So the right side it is 0, left side is 1. L mu, this is 1, 1, nu E bar is minus 1, yes. So this is sorry, for this, here also this is 0. So for, since we are discussing the lepton number associated with the muon, this is 1. Since this is electron, this is 0. This is an antineutrino, this is 0. Associated with the electron, this is 0. Since it is a neutrino associated with muon, this is plus 1. So right side 1, left side 1. So the change in delta L mu is 0. If you take a Le for muon, this is 0. Electron, this is plus 1. Antineutrino minus 1, and this is 0. So left side and right side is 0, so delta Le is 0. Therefore, the charge is conserved and the lepton number is conserved. Therefore, this is a possible reaction. Now, if we take problem 3, pi minus plus p plus and this reaction, after the reaction, the particles are sigma minus plus k plus k0. Some people call psi particle xi. Xi particle, some call this is a cascade particle, both are same. Now here the charge, here this is a charge conservation that can be easily found from this symbol itself. Since this is a minus symbol, this is minus, here P plus, this is a proton, so this plus, so minus plus, here this is a minus, therefore this is a minus 1, this is plus 1, 0, 0. So delta Q is equal to 0. So the charge conservation can be obtained very easily. Now, since they are baryons, so these particles are baryons. So, for baryons, the baryon number is 1. So, this since this is pi is this is a meson for meson baryon number is 0, for baryons baryon number is 1. So since it is a meson and the baryon number is 0, P is a baryon, therefore the baryon number is 1, and psi minus this is a baryon, so this baryon number is 1, and K plus K0, they are meson, for meson baryon number is 0, therefore this is 0 and 0. So here you can find the total baryon number before the reaction and the after reaction, both are same. So delta B is 0. Now let us find the isospin quantum number I for minus B, pi minus. Now here if we want to find I, 2I plus 1 is the total number of particles in a group. So this is since it is a pi, there are 3 particles in the group, pi plus, pi 0, pi minus, that belongs to a subgroup. So there are 3 particles. 2I plus 1 is equal to 3, therefore 2I is equal to 2, so I is equal to 1. So I is equal to 1. So since you know the group, so from this you can say this belongs to one group, the particles in the horizontal line belongs to one group. So this is one group, this is the same group, and this is same group, and so on. So the particles belong to the horizontal line belongs to a group. So from the diagram itself you can see I must be 1, and P there are 2 particles. There are 2 particles, 2I plus 1 is equal to 2, so I must be equal to half, so I is equal to half. So similarly for xi minus is what? Xi minus, now here there are 2, this belongs to a single 2 particles in a group, so I is equal to half. K plus K0, this belongs to one group, so this is half. So once if you find the I value before reaction is 1 by 2, 1 and a half, after the reaction it is also 1 and a half, so delta I is equal to 0. Find I3. I3 can be determined for using this formula, or I3 can be directly determined from your diagram. So this is for pi minus. For pi minus, what is I3? This is a minus half, this is minus 1. So that's why the diagram is very important. Look at the diagram, you find the value of I3, and this is minus 1. So you can, this is I3 as well as T3. So some others use T3, some others use I3. So I3 is equal to, this is a minus 1. Similarly find I3 corresponding to P. This is P, this projection. So this is I3 is half. So you substitute a half value. Similarly for particle on the other side, sigma minus K plus K0, you substitute the I3 values from the diagrams, and you will see that delta I3 is 0. So strangeness quantum number. Strangeness quantum number, the pi and P, they are mesons, and this is nucleons. They are not strange particles. So only the strange particles are this. So remember, these are the strange particles. Strange particles alone will have strangeness quantum number. For other particles, the strangeness number is 0. Therefore, this is 0, 0. Whereas psi minus 1, what is the strangeness number? The strangeness number is y minus b. So y is equal to b plus s, y minus b. So from the diagrams you can easily see this is xi minus, this is xi minus, what is the value? The value is of y is minus 1, y is minus 1, and all are baryons. So baryon number is 1. So minus 1 is equal to minus 2. So this is the strangeness number. So strangeness number can be calculated also from the diagram. So from the diagrams you find the y value. That so for you look at this one, the y coordinate is your y value, and they all are baryons. For baryons, the baryon number is 1. So you subtract this one, you will get a S value. Here for mesons, this is the y value, and baryon number is 0. Baryon number is 0. So if you want to find the strangeness number, you need not subtract minus 1 there, whereas for baryons, for these two group, you have to subtract y value from minus 1. For baryons it is 0. Now we take the fourth example, which is pi minus plus p plus, which is equal to lambda 0 plus k 0. Now you write down the charge value on both sides, this minus 1 plus 1, here 0 0, delta q 0. B value, this is a meson, therefore this is baryon number is 0, proton this is plus 1, the other side lambda 0 k 0, k 0 is a meson, this is 0, lambda 0, this is a baryon, this is 1. So both right and left side, the both are the baryon number is equal, therefore delta B is 0. For isospin number, we have already mentioned for pi particles, pi meson, I value, I is always a positive number, so this is 1. For p is a half, lambda 0 is 0, k 0 is half. Now here delta is not equal to 0. Whereas if we take I3, if I is equal to 1, I3 will be, we have three values. Pi plus, this is a plus 1 value, pi 0, I3 is 0, for pi minus it is minus 1. So this is minus 1. This can be also found from this deck. This is minus 1. Pi value, y value is minus 1, baryon number is 0. So minus 1 minus 0, which is minus 1. So from this diagram also you can write down the I3 values. Minus 1, for p this is a half, and lambda 0, this is a 0, and k 0 is for k 0, this is a value. Minus half. So on the right side, left side, both are equal, delta I3 is 0. Similarly, the strangeness number can be also determined from this diagram, or you can use this formula. Either way, or if you remember this value, because the strangeness number is also given here, you can, if you remember these values in your mind, you can directly use this value. Otherwise, you have to use the diagram. So if you use the diagram, it will be much more convenient. So delta S is also 0. So Q, B, I3, S. In all these quantum numbers, delta I is not 0. If delta I is not 0, I is a weak quantum number. So since I is a weak quantum number, in some cases there is a consideration of isospin. Some cases it is not conserved. Even if it is not conserved, the reaction is allowed. So since it is a weak quantum number, you may just forget about this. You check where the remaining numbers are, the remaining these quantum numbers are, the conservation is satisfied for the remaining numbers, then you can say this is a reaction, is an allowed reaction. So this is a allowed reaction, even though this delta I is not 0 because it is a weak quantum number. You take another case, another problem, fifth one, pi minus plus p plus, which results in sigma plus k minus. So find q value, this is minus, plus, minus. So delta q is 0. B, this is meson 0, this is a baryon plus 1, this is for baryons plus 1, k is a meson 0. So both sides delta B is also 0, I is equal to 1 by 3, 1 half delta I is 0, and I3 is not satisfied because this is a minus 1, for this one plus 1, whereas here 1 minus half, so this is this side minus half and this is plus half, and therefore delta I3 is not 0. So the third quantum number, also the isospin is not conserved. And similarly find the strangeness number. This is not, they are not the strange particle, this is S is 0. Here this is sigma minus 1, k minus it is also minus 1. So delta S is not also 0. So since these two quantities are conserved, this reaction is not possible. Now let us discuss some more problems. Now let us check whether the following quadrant numbers Q, L, B, there are 6 quadrant numbers, P, I3, S. Whether the 4 quadrant numbers are conserved. So this is the conservation loss. There are a conservation loss corresponding to all the 6 numbers. So now let us take the first one, P plus N, so minus plus K plus sigma plus. Now let us check all the quadrants are satisfied. So the first one is Q. Charge, this is plus 1, this is 0, here this is charge is minus 1, plus 1, plus 1. So the charge is conserved. Charge is conserved. If we take baryon number, this is a baryon, this is a baryon, baryon number 1 1, and this is equal to also a baryon number. Since this is a meson, this is a baryon, so baryon number is also conserved. And if we take isospin, for P this is half. If you have any doubt, you can use this formula or you can look at the diagram. The diagram is much more important. It gives all the information. So whenever a problem asked in this type, you first draw the diagram, and from the diagram you can get all the information. So I is equal to half. Here this is for n also, this is I is equal to half. Whereas here for sigma minus, this is a half, K minus half, and this is a plus 1. Now once if we add on both sides, the numbers are not equal, so the conservation law is not satisfied for isospin quantum number. If we take I3, this is half and this is minus half. So from the diagram you can see, this is plus half and this is minus half. So I3. And here for psi minus, so for psi minus this is minus half, for K plus this is plus half, for sigma plus this is plus 1. So the I3 is also not satisfied, conservation of I3 is not satisfied, and you take S, strangeness quantum number, since they are not strange particles, so the strangeness quantum number is 0, and here for sigma minus, y is equal to minus 1, y minus b is S, b is also 1, so minus 1 of minus 1 is minus 2, so this is minus 2. So similarly for K plus, this is minus 1. What is K plus? So this is K plus, this is a y, this is a y minus b is 0, so this is plus y. So this is a plus 1. For sigma plus this is 1, and so for sigma plus this is 0, y value is 0, and 0 minus 1 is minus 1. So the S number is minus 1. So again you see this is not satisfied. So these quantum numbers are conserved, Q and B, whereas I3, S, they are not conserved. Now you will take the next problem. you take the second problem. Pi minus plus p plus minus plus k plus k0. So first check the q value, minus 1 plus 1 minus 1 plus 1 0. So the q value is satisfied. Both sides q are 0, delta q is 0. Therefore this is conserved. If you take this b, this is the meson 0, baryon number is 0. Here p is a baryon, so baryon number is 1, and this is a baryon number is 1, and these are meson particles. So this both sides are 1, so the baryon number is also conserved. And if we take I value, here this is 1 and this is half, and here psi minus is, what is I? I can be determined from here. So from this I is equal, this is half, k plus is half, k0 is half. This is I value. So there are there are 2 particles in the group. So if you substitute 2 here, this I will be 2i plus 1 is equal to 2, so I is equal to half. Similarly for this is also half. So this is 1 and half, and this is 1 and half, so I is also constant. So using this formula I can be determined. And find I3. I3, what is pi minus for I3? This is your I3 axis, so pi minus is minus 1. So this is minus 1 for p plus. For p plus this is half. So this is half. Xi minus, this is minus half plus, what is k plus? For k plus it is plus half. K0 is minus half. So the right side minus half, left side is minus half, so delta I3 is also conserved. And the S number, strangeness, they are not strange particles, so this is 0 0, or psi minus is a strange particle, and the strangeness number is minus 2. So that can be determined S is equal to y minus b. Y can be determined from the psi minus is y value is equal to the hypercharge. Y value will be for which particle? Psi minus. For psi minus, this is already minus 1, minus 1, minus of minus 1, minus 1, minus of baryon is 1. So minus 1 minus of 1, which is equal to minus 2. Therefore strangeness number for this particle, the cascade particle, is minus 2. For k plus k0, this is 1 and 1. Our k plus and ky, their y value is 1. For this also y value is 1, but since baryon number is 0, so S is equal to y value itself. So now both sides you find this is S is 0, here S is 0. So here all these numbers Q, B, I, I3S, all the 5 quantum numbers are conserved. Now let us take a problem like this, pi minus plus p plus lambda 0 plus pi minus. So take a q, this is minus 1 plus 1, 0 minus 1. So q is not conserved. So this q is not. Once if q is not conserved, this is not an allowed reaction. You can simply write this is not an allowed reaction. So even if the other numbers are conserved, q is not conserved, the reaction is not allowed. B is equal to Here you can find this 0 plus 1, this goes to 1 plus 0, this is allowed, and I will be 1 plus half, and this is 0 plus 1. So this is not conserved, and I3 from the diagram you can easily take the numbers for I3 corresponding to all the particles. This is minus 1 plus half, this side 0 minus 1 not conserved. S value is here minus 1 plus 0, here minus 1 plus 0. So S is conserved. Since Q and I3 are not satisfied, they are not allowed reaction. So now let us take one more problem. Yeah. If we take pi minus p plus lambda 0 plus pi minus. This is we have already discussed this problem. We take this. So Q here minus 1 plus 1 plus 1 minus 1. So this is satisfied. Barrier number, this is 0, this is a meson, and this is 1, this is 1,